Okay, thank you for this introduction. So as Simon already announced, the title of my presentation is N-type doping of metal halide perovskites through dopant oxidation. And I thought I would introduce myself before. Why did it block? Okay. So I thought that before I start talking about perovskites, I will talk about myself for a couple of seconds. So I come from Poland, but I love Italy, so I didn't miss an opportunity to go there, even if it was for studying. So I did my first internship in Palermo, in Sicily, South Italy, and then I spent one semester of Erasmus at the University of Florence. After my master's, during which I worked at Polish Academy of Science, I moved to Bordeaux for a PhD, and today you will listen to some of the results, the presentation of some of the results from my PhD. And after I finished my PhD at the end of last year, I stayed for a postdoc at the same institution. So today's presentation, I divided into 4 sections. First, the introduction, of course, then I will talk about my approach for doping using metastable ions. Next, I will talk about the characterization of the doped perovskite layers, and I will finish with conclusions and perspectives. So Vincent told me that everybody knows perovskites here. Then I will just bring up quickly some of the applications of perovskite semiconductors. Also, I would like to notice here that we are, I hope, at the beginning of the new generation of the perovskite development that is associated with the perovskite doping. And this could bring us the advantages of silicon with, this could combine the advantages of silicon, where we have well-controlled doping, with the advantages of perovskite, such as low costs and the possibility of printing perovskite layers on flexible substrates. This could also enable to make a fully perovskite transistor, and these are just some of the exciting options that we have once we control the doping. However, the story of perovskite doping is not as simple as in case of silicon because of the ionic character of the perovskite crystal. So if we want to introduce the heterovalent dopants into the perovskite crystal lattice, just like we do in case of silicon, we will encounter the presence of the counterion that will cancel the effect of doping. Therefore, some alternative approaches have to be applied. And one of these approaches is derives from the organic semiconductors, and it is molecular charge transfer doping. In this example, we have a F4 TCNQ molecule that has the LUMO level lower than the valence energy of the perovskite, and this enables an efficient Hall transport, resulting in the shift of the Fermi level towards the valence energy, and the conductivity increase by around 5 orders of magnitude, which is accompanied by the increase of Hall density. This is one of the best examples of doping with the highest increase of conductivity so far. And this is, of course, for p-type doping. When it comes to heterovalent doping, there was an attempt in 2016 to dope single crystals of methylammonium lead bromide with bismuth 3+. And in this case, we can see already that in this graph, we can see that the doping was actually very inefficient, but it's expected for perovskites for the impurities to be very difficult to introduce, because since we are dealing with the ionic crystal, this is some sort of self-purifying system. So naturally, impurities must be very difficult to introduce. And here we observe that the amount of bismuth in the crystal is just a fraction of the amount of bismuth introduced in the feed solution. Nevertheless, the increase of conductivity was observed by around 4 orders of magnitude, and the increase of majority charge carrier concentration by around 2 orders of magnitude. And this was concluded to be due to the narrowing of the bandgap. As we can see here, the color of the crystal darkened, and this was associated to the narrowing of the bandgap, which was, of course, also supported by the UV-Vis absorption spectra. Nevertheless, 2 years after that, the group of Professor Miyasaka made a similar sample and measured the photoluminescence. And they showed that photoluminescence peak occurs exactly at the same energy for all the doping concentrations. It means that the bandgap doesn't really change. What they observed was the decrease of the photoluminescence peak intensity and the widening of the peak, which is normally associated with the increase of the defects in the crystal lattice. From this, we can conclude that the increase of conductivity that was observed in this experiment probably comes from the increase of the defects localized close to the band edges. So as you can see, heterovalent doping is a very tricky one. So for my PhD thesis, we had a little bit also tricky approach. So the approach that we used was to substitutionally to substitute lead, so to dope substitutionally, and to use homovalent dopant, so 2+ metal, but we wanted to choose the metal that would be metastable. So once introduced into the perovskite crystal structure, it would oxidize to 3+ and release 1 electron to the conduction band. This electron obviously would increase the electron density, leading to the shift of the Fermi level, leading to the N-type semiconductor. So this sounds great. And for this, we had to select the right dopant. So there are 2 criteria that had to be followed. The first satisfied. The first criterion was obviously the metastability of the dopant at the 2+ and stability at the 3+. And the second was the size of the ionic radius. In this table, I presented some of the potential candidates with the ionic radius similar to the ionic radius of lead 2+. And today I will present the results of for samarium. So in the first experiment, I mixed the precursors of the perovskite together with the precursors of the dopant. So in this case, samarium 2 iodide. Spin coated them, annealed obviously, and I measured the lateral conductivity with symmetrical gold electrodes. And I observed a slight increase of conductivity, let's say up to 9 times increase of conductivity, but also a big spread of results. So we thought that there is water in the lead precursor and everything happens in DMF. Samarium iodide is known to be very reactive and doesn't like moisture, definitely. So how about we make the perovskite first, and then once everything is dry and clean, then we introduce the dopant. So that's exactly what I did. So I called it 2-step doping with samarium. So first I spin coat perovskite, and I spin coat samarium iodide, and anneal again. The conductivity of the sample prepared that way increased by around 2 orders of magnitude compared to undoped. And also I measured as a control the conductivity of the layer of samarium iodide alone to make sure that the increase of conductivity comes from the combination of the perovskite and the dopant, and it's not just the conductivity of the dopant alone. By scanning different doping concentrations, I reached around 3 orders of magnitude increase in conductivity, and I observed the increase of conductivity in all the experiments that I performed. So it was a very reproducible method. So once I knew the right dopant and the right method for doping, here comes the time to characterize the layer and to answer some questions. So the first question was the valency of the dopant. And for this, typically we use XPS. Other dopant characterization that I did was the atomic profile using also XPS edged with argon clusters and ToF-SIMS. I performed some complementary characterization that includes the investigation of the topology of the sample, crystal structure, so XRT. Also, I made UV-vis absorption, spectra, and photoluminescence. And as last, I made the investigations of the electrical properties, such as surface potential difference, UPS, and also charge carrier density using Mott-Schottky and Hall effect. So the first question that I already mentioned was about the valency of the dopant. So for that, I did the XPS of the samarium iodide layer. And here, obviously, we notice, unfortunately, we already have samarium 3+ in our samarium 2+ dopant. It's probably due to very high reactivity of samarium iodides. Well, it's unavoidable. Nevertheless, there is still a substantial amount of samarium 2+. And what's important, this samarium 2+ peak is not present for on any of the doping concentration. Another thing is that the peak associated to samarium 3+ shifted towards higher binding energies, suggesting different environments of the samarium in the samarium iodides and in the perovskite layer. And this is a very nice hint that samarium might actually really be incorporated into the perovskite crystal structure and not stand as a mixed phase samarium iodide and perovskite. As a control experiment, I also prepared samarium 3 iodides, and I doped the perovskite layer using the same technique, and I observed none to insignificant increase of conductivity in this case, showing again that it must be samarium 2+ and not 3+ to use for the doping. 1 second. The same technique, XPS, was used to investigate the atomic composition in the atomic profile of the perovskite, of the doped materials. And here we can see, both on XPS and on ToF-SIMS profiles, we can observe an increased amount of samarium close to the surface, which is perfectly justified by the method used for the doping. Nevertheless, there is a substantial amount of samarium close to the bottom of the layer, and this was confirmed by both techniques. Using the XPS, we calculated that the amount of samarium is around 21%, which corresponds to 10 to the power of 20 per centimeter square dopant density, which is in fact a little high for the standard definition of doping. Therefore, we investigated further. But before that, we investigated the topology of the sample, and we can see that, as expected, the surface was changed upon doping. There are probably some residues of samarium iodide or samarium oxide on the surface. And the 0 milligram per milliliter, I forgot to mention earlier, This is the sample that is treated with the solvent of some barium iodides, just to make sure that the solvent alone doesn't alter the properties of the perovskite. So regarding other key properties of perovskites, here we have the XRD pattern, and it shows a typical MAPI tetragonal pattern that doesn't change upon doping, except for the highest doping concentrations, where we clearly can see some peaks that stand for most probably phase separation of phase separation. And this probably stands for a decrease of conductivity for the highest doping concentration. Another very interesting thing we can see after zooming in to the principal peak of the samples that show the increase in conductivity. And here we can see that the principal peak shifted a little bit towards lower angle. This shows probably lattice expansion upon doping. And from this, we can conclude or guess that probably the dopant, introduced dopant, is in the valency of 2+, causing lattice expansion, and after crystallizing, it oxidizes to 3+. This is one of the possible explanations. Other key properties, just like bandgap, were also measured from the UV-vis spectra. And this is also typical for MAPI and didn't change upon doping. Photoluminescence occurs at 780 nanometers, which is also typical for MAPI. And also we observe a complete quenching of the photoluminescence signal for all the doping concentrations that we discussed so far. As much as this is perfectly consistent with doping, it was interesting to investigate what happens for the intermediate doping concentrations. So for this, I also prepared 1/2, 0.1, and 0.05 milligrams per milliliter doping. And we can observe, in fact, partial quenching for 1 and 0.5 milligrams per milliliter. But interestingly, for very low concentrations, such as 0.1 milligrams per milliliter and 0.05, we observe an increase in the photoluminescence peak intensity. This can originate from two phenomena. One is that extra electrons, a small amount of extra electrons injected into the perovskite structure, fill the traps, and this leads to the higher photoluminescence. And another is that in some reports, MAPI, undoped MAPI, is a little bit p-doped. And if this is the case, then injection of extra electrons would shift the Fermi level more towards the intrinsic semiconductors. Yes. So now one of the most interesting parts, the investigation of the semiconductor type, which can be typically done with using UPS. And from the onset of the UPS spectrum, we can find the work function. And here we can see that the work function decreases with the doping concentration. However, we have to remember that just the decrease of the work function doesn't necessarily mean N-type doping. For this, to ensure this, we have to take a look at the valence band region. And in this case, we can observe that the absolute value of the energy with respect to the Fermi level increases with the doping concentration. I took these two results together and I put them on this graph to make it all clear. And from this, we can see that the Fermi level of the undoped MAPI falls almost exactly in the middle of the bandgap. And we can observe a slight shift of the Fermi level towards the conduction energy as the doping concentration increases. And for 10 milligrams per milliliter, we can observe around 0.5 electron volt shift towards the conduction energy. Also, we can observe a small surface dipole of around 0.3 electron volts. And this is probably due to the doping method and the residues of samarium species on the top, which we could observe, for example, on the IFM and SEM images. So now let's go to the investigation of the charge carrier density. And for this, there are two techniques that I used. One is Hall effect and the other is Mott-Schottky. So to measure the Hall effect, we collaborated with a Semilab company from Hungary. And we measured my sample in the Hall bar configuration. Now the Hall effect, probably most of the people know, but just to remind, it's the effect on the semiconductor or conductor where the charge deflects in the magnetic field when in the flow of current. And so when we have this deflected charge, we can measure the difference, potential difference, so voltage. And this voltage is obviously proportional to the current and to the magnetic field, inversely proportional to the thickness. Also, there's a proportionality factor that's called Hall factor, and this Hall factor is proportional to the scattering factor that is experimentally assumed to be around 1 for most cases, and to the charge carrier density. So in the scenario that I just described, this is called a static Hall effect. But for highly resistive samples, such as perovskite thin films, by making just this measurement, it would be impossible to distinguish signal from noise. And therefore, typically we apply an alternating magnetic field in order to distinguish the signal from the noise. So we applied here my alternating magnetic field, and we read the alternating resistance signal. And from this, the semiconductor type was found to be N-type, good news. And the charge carrier density was calculated to be at the order, well, at the level of 10 to the power of 13 per centimeter cube. Now, this value is in agreement with other literature values for similar systems, doped and undoped, but it's much lower than the example of molecular charge transfer doping with F40SynQ that I mentioned at the beginning. This discrepancy is it's an investigation work in progress, and we are still working on explaining why there are so many discrepancies in the literature, and voila. So knowing this technique needs a little bit more focus, we moved to the Mott-Schottky analysis. And Mott-Schottky is based on the fact that on the semiconductor metal junction, we create a depletion layer. And now this depletion layer will change its thickness depending on the bias that we apply. And we can consider this depletion layer between metal and semiconductor, we can consider it a capacitor. So this depletion layer thickness will depend, of course, on the bias, but also on the ionized dopant density. And therefore, by plotting the inverted C-square, against the voltage. From the slope of this plot, we can calculate the ionized dopant density. In collaboration with Dr. Bastien Politi and Professor Raphael Clerc from Saint-Étienne, we measured the capacitance as a function of voltage for the perovskite layer sandwiched between tin oxide, which created an ohmic contact for electrons, and gold. Now, between gold and perovskite, we inserted an ultra-thin layer of insulating PMMA that had the purpose of decreasing the leakage current. Well, here are the Mott-Schottky plots, so we can observe the decrease of the slope for an increase of doping concentration, and this corresponds to an increase of ionized dopant density. I plotted this ionized dopant density against the doping concentration, and we can see that the ionized dopant density is in the level of 10 to the power of 17, while the doping concentration calculated from the XPS is on the level of 10 to the power of 20. So in order to elucidate this discrepancy, I measured the conductivity as a function of temperature in order to calculate the activation energy of the dopant. And here, the first thing we can observe that at room temperature, the activation energy for doped and undoped perovskite is very, very similar. It's around 100 milli-electron volts. So we can see that the conductivity increased, but the slope, so the activation energy, didn't change. This leads to the conclusion that at room temperature, the main obstacle for the charge, so the main limiting factor of the charge transport is probably grain boundaries. Below room temperature, at lower temperatures, charges can tunnel through the grain boundaries, and therefore we can read, let's say, the real activation energy of the dopant. And this one was calculated to be around 350 milli-electron volts. So to make sure, to confirm this theory, we asked Bastien and Raphael to simulate Mott-Schottky plots for different activation energies. And so we can see this solid gray line represents a zero activation energy. So all the dopant that is introduced to the structure is to the perovskite is activated, and result in it is in fact the ionized dopant. So we have 100% here. Then as we increase the activation energy, this let's say this curve flattens and the slope increases, and we can observe that less of the introduced dopant is ionized. By probing the density found in the XPS for the activation energy calculated from the Arrhenius plot, so 350, we can see that the level of the ionized dopant density is around 10 to the power of 17. So this shows that at room temperature, most probably the majority of the dopant is freezed out. There's a freeze out phenomenon that occurs. So conclusions. I developed a method to dope substitutionally MAPI thin film using metastable ions, which results in N-type doping. This led to the conductive conductivity increase by around 3 orders of magnitude. And the dopant is present all throughout the layers. Bandgap didn't change, and also photoluminescence quenching was observed. When it comes to transport properties, at room temperature, transport mainly occurs at grain boundaries. And the ionized dopant concentration at room temperature is around 10 to the power of 17 per centimeter cube. So this is the one step towards the new generation perovskites, doped perovskites, where we can create devices based on p-n junction, and this can open new chapters for electronics, and notably transistors or photodetectors. So there's an open field for plenty of devices. So I would like to acknowledge my supervisors from my PhD, Lionel Hirsch, Dario Bassani, and Sylvain Chambon. This is our team and research funders. And thank you very much. And I can see that there's already a question.